Deep in the vastness of space, something extraordinary has caught the attention of astronomers around the world. Something that defies our understanding of how the universe should work. As we journey together tonight through this cosmic mystery, we'll explore an object so unusual, so unprecedented in its behavior, that even NASA has remained curiously silent about its true nature. This is the story of 3I Atlas, a visitor from beyond our solar system that refuses to follow the rules. What makes this discovery truly remarkable is not just where it came from, but what it's doing now, and what that might mean for everything we thought we knew about the cosmos. So settle in, take a deep breath, and let us drift together into one of the most puzzling mysteries of modern astronomy. Imagine for a moment that you're standing in your backyard on a quiet evening, watching the stars, when suddenly you notice something that shouldn't be there. A light moving in a way that makes no sense, behaving unlike anything you've ever seen before. This is essentially what happened when astronomers first detected 3I Atlas in the winter of 2024. But this wasn't just any unusual object passing through our cosmic neighborhood. This was something that had traveled from another star system entirely, crossing the incomprehensible distances between the stars to visit our little corner of the galaxy. And from the very beginning, it was clear that something about this visitor was different. Scientists have recently uncovered something extraordinary about this interstellar traveler, and the more they observe it, the stranger it becomes. The designation 3I tells us something important right away. It means this is only the third interstellar object we've ever detected passing through our solar system. Think about that for a moment. In all of human history, with all our telescopes and satellites and advanced technology, we've only spotted 3 confirmed visitors from other star systems. The first was Oumuamua in 2017, which itself sparked years of debate and speculation. The second was 2I Borisov in 2019, a comet that, while unusual for being interstellar, at least behaved relatively normally. But 3I Atlas, this third visitor, is proving to be something else entirely. As we continue our exploration of this mystery, you'll begin to understand why this object has astronomers losing sleep and why NASA's relative silence on the matter has only deepened the intrigue. What we're about to discover will amaze you, because 3I Atlas isn't just unusual in one way. It's unusual in multiple ways, all at once. Its trajectory doesn't quite match what we'd expect from a simple piece of cosmic debris drifting through space. Its brightness fluctuates in patterns that seem almost deliberate. Its composition, as far as we can tell from spectroscopic analysis, contains elements in ratios we've never quite seen before, and perhaps most puzzling of all, it appears to be accelerating. But not in the way a comet accelerates, when the sun's heat causes ice to vaporize and create thrust. No, this acceleration is different. It's subtle, yes, but it's there, and it follows a pattern that has left some of the world's brightest minds scratching their heads in bewilderment. Let's take a moment to imagine what it means for something to be truly interstellar, because our brains didn't evolve to comprehend these distances. The nearest star system to our Sun, Alpha Centauri, is about 4.37 light-years away. That means if you could travel at the speed of light itself, the fastest speed possible in our universe, according to everything we know about physics, it would still take you over 4 years to get there. For an object traveling at normal cosmic speeds, the journey from another star system to ours would take tens of thousands, if not hundreds of thousands of years. 3I Atlas has been traveling through the cold darkness of interstellar space for longer than human civilization has existed. And now, for this brief moment in cosmic time, its path has intersected with ours, allowing us to observe it, study it, and wonder about its origins. The implications of this are staggering when you really stop to think about them. Every interstellar object that passes through our solar system is like a messenger from another world, carrying information about star systems we may never be able to visit. These objects were formed around other suns in conditions that might be completely different from what we experience here. They might contain materials or chemical compounds that don't exist anywhere in our solar system. They might even, and this is where the mystery deepens considerably, contain something more. Something that would fundamentally change our understanding of our place in the universe. Scientists are understandably cautious about making dramatic claims, but the unusual behavior of 3I Atlas has forced many to consider possibilities they might have dismissed just a few years ago. As we journey deeper into this mystery, it's worth noting that the discovery of 3I Atlas itself was almost accidental. The Atlas Survey System, which stands for Asteroid Terrestrial Impact Last Alert System, is designed primarily to detect potentially hazardous asteroids that might pose a threat to Earth. It consists of 4 telescopes spread across Hawaii and South Africa, constantly scanning the night sky, taking image after image, looking for anything that moves against the background of stationary stars. On that fateful night in early 2024, one of these telescopes captured something unusual. At first, it looked like it might be just another asteroid or comet from the outer reaches of our solar system. But as more observations came in over the following nights, astronomers realized they were looking at something far more special. Something that was moving on a trajectory that could only mean one thing. This object had come from interstellar space. The excitement in the astronomical community was immediate and intense. News spread quickly through professional networks, and telescopes around the world were rapidly reoriented to capture as much data as possible before this visitor disappeared back into the depths of space. Every hour of observation time became precious. Every spectrum, every image, every data point could reveal something new about this cosmic traveler. But as the data accumulated, the excitement began to mix with confusion. Because what they were seeing didn't quite match any existing models or theories. 3I Atlas was breaking the rules, or perhaps more accurately, it was revealing that our understanding of the rules was incomplete. And that's when the real mystery began. That's when some astronomers started asking questions that made their colleagues uncomfortable. And that's when NASA's peculiar silence on the matter started to seem less like bureaucratic caution and more like something else. What makes the story of 3I Atlas even more intriguing is the historical context in which it appears. Let's drift back in time for a moment. Back to October 2017, when humanity got its first confirmed glimpse of an interstellar visitor. The object that would come to be known as Oumuamua, a Hawaiian word meaning scout or messenger from afar, was spotted by the Pan-STARRS telescope in Hawaii as it was already leaving our solar system. This in itself presented a challenge. Astronomers had only a limited window to study it before it disappeared forever into the darkness between the stars. What they observed during that brief time sparked one of the most fascinating debates in modern astronomy. Oumuamua was strange from the very beginning. Its shape was unlike anything we'd seen before, highly elongated, perhaps 10 times longer than it was wide, tumbling through space like a cosmic cigar. But what really caught everyone's attention was its acceleration. As Oumuamua swung around the sun and began its journey back out of the solar system, astronomers noticed it was moving faster than it should be based purely on the sun's gravity. Something was giving it an extra push. For a comet, this would be easy to explain. Ice on the surface vaporizes as it approaches the sun. creating jets of gas that act like tiny rocket engines. But Oumuamua showed no signs of such outgassing. No tail, no coma of gas and dust, nothing that would indicate it was a typical comet. So, what was accelerating it? The debate that followed captured the public imagination in ways that few astronomical discoveries do. Scientists proposed various explanations. Perhaps it was made of hydrogen ice, which would vaporize without creating a visible tail. Perhaps the outgassing was asymmetric in a way that made it hard to detect. Perhaps it was covered in some kind of dark coating that trapped heat and caused unusual thermal effects. These were all reasonable, if somewhat speculative, scientific hypotheses. But then came the more provocative suggestion, one that many scientists were reluctant to even discuss publicly. What if Oumuamua wasn't entirely natural? What if its unusual acceleration was because it was, in some way, artificial? This suggestion, put forward by respected Harvard astronomer Avi Loeb, was met with intense skepticism by most of the scientific community. And yet, it couldn't be entirely ruled out based on the data we had. Oumuamua had already left the solar system. We would never get another chance to study it more closely. The mystery would remain unsolved. As we continue our exploration of this story, it's important to understand why Oumuamua matters to our understanding of 3I Atlas. Because when the second interstellar object, 2I Borisov, was discovered in August 2019, many astronomers breathed a sigh of relief. Finally, here was an interstellar visitor that behaved normally. 2I Borisov was clearly a comet, with a beautiful tail of gas and dust streaming behind it as it approached the sun. Its acceleration could be easily explained by standard cometary outgassing. Its composition, while coming from another star system, was broadly similar to comets in our own solar system. In many ways, 2I Borisov seemed to validate the idea that Oumuamua had simply been an unusual but ultimately natural object. Perhaps a fragment of a planet torn apart by tidal forces, or a comet that had lost most of its volatile materials during previous passes near other stars. The universe, it seemed, was returning to normal. Interstellar objects existed, yes, and they were fascinating to study. But they weren't going to fundamentally challenge our understanding of the cosmos. And then came 3I Atlas, and suddenly, nothing seemed quite so certain anymore. Let's take a moment to imagine the scene at various observatories around the world as data on this new object began to accumulate. Picture teams of astronomers, many of them veterans who had studied Oumuamua and 2I Borisov, staring at their computer screens with expressions of growing bewilderment. The trajectory was strange, not quite hyperbolic in the way a typical interstellar object should be, but not elliptical like something bound to the sun either. It was something in between, something that suggested this object had somehow adjusted its path. The brightness variations were peculiar too, showing patterns that didn't quite match the simple tumbling motion you'd expect from a natural asteroid or comet. And then there were the spectroscopic readings, the chemical signatures that told us what the object was made of. These showed something that had astronomers quietly messaging colleagues in the middle of the night, unsure if they should believe their own instruments. What we're about to discover will challenge everything we thought we knew about interstellar space. Because the more data that came in about 3I Atlas, the more it seemed to defy easy categorization. It wasn't quite like Oumuamua. It showed some signs of cometary activity, a faint coma of material surrounding it, suggesting it wasn't a bare rock tumbling through space. But it also wasn't like 2I Borisov either. The outgassing was asymmetric in ways that couldn't be easily explained by the object's rotation or shape. The chemical composition included organic compounds, carbon-based molecules, in abundances that seemed unusual even for a comet from another star system. And most puzzling of all was the acceleration pattern. It was accelerating, yes, but the direction and magnitude of that acceleration didn't quite match what you'd expect from cometary outgassing alone. It was as if something else was at work, some additional force or mechanism that we didn't yet understand. Scientists have recently uncovered something extraordinary in the detailed analysis of 3I Atlas's light curve, the pattern of how its brightness changes over time. When an irregularly shaped object tumbles through space, its brightness should vary in predictable ways as different surfaces catch and reflect the sun's light. This is simple geometry and physics. But 3I Atlas's brightness variations included periodic components, regular, repeating patterns that seemed too precise, too regular, to be explained by random tumbling alone. Some astronomers began to whisper about what this might mean. Was the object's shape more complex than a simple, irregular rock? Did it have structural features that created these regular patterns? Or was something even more unusual happening? These questions might seem abstract, but they cut to the heart of a profound mystery. Whether we are observing a natural object shaped by cosmic forces, or whether we might be glimpsing something that challenges our assumptions about what exists in the universe. Deep in the vastness of space between the stars, conditions are harsh beyond our everyday comprehension. Temperatures hover just a few degrees above absolute zero, the coldest possible temperature where all atomic motion nearly ceases. Radiation from cosmic rays constantly bombards anything traveling through this void, slowly altering its chemistry and structure over millions of years. There is no air, no sound, no weather, just the endless cold darkness punctuated occasionally by the distant light of stars. Any object traveling through this environment for tens or hundreds of thousands of years would be profoundly affected by these conditions. It would be sandblasted by microscopic dust particles traveling at enormous speeds. Its surface would be darkened and altered by radiation exposure. If it contained any ice or volatile materials, these would slowly sublimate away into the vacuum of space. By the time such an object reached our solar system, it should be an ancient, weathered thing. Its surface dark and pitted, its interior transformed by eons of exposure to the interstellar environment. As we journey deeper into this mystery, we need to consider what all this means for 3I Atlas. Based on its trajectory and speed, astronomers have calculated that this object has likely been traveling through interstellar space for at least hundreds of thousands of years, possibly much longer. It has survived this unimaginably long journey through conditions that would destroy most human-made materials within decades. And yet, when we observe it now, as it passes through the relative warmth and light of our inner solar system, it appears to be active. It's releasing material, changing in brightness, possibly even altering its trajectory in subtle ways. This level of activity after such a long journey is itself somewhat surprising. Most comets in our own solar system become less active over time as they make repeated passes near the sun and gradually lose their volatile materials. How has 3I Atlas retained enough volatiles to still be active after such an extended journey through interstellar space? This is one of many questions that keep astronomers pondering long into the night. The implications of this are staggering when we consider what it might tell us about the nature of interstellar space itself. Perhaps the region between the stars is not as empty as we thought. Perhaps there are clouds of material, hydrogen, dust, even complex organic molecules that could accumulate on an object's surface during its long journey, effectively replenishing some of what it loses to radiation and sublimation. Or perhaps 3I Atlas, formed in an environment around its parent star, that somehow made it more resilient, more capable of retaining volatiles over vast timescales. Some astronomers have even speculated that the object might have spent much of its journey in a dormant state, its volatiles locked away beneath a protective crust, only to become active again when it entered the warmth of our solar system. Each of these possibilities opens up new questions about the nature of interstellar objects and the environments that produce them. Let's take a moment to imagine what the parent star system of 3I Atlas might have been like. Somewhere out there, perhaps 50 or 100 light-years away, perhaps even farther, there exists a star around which this object once orbited. Was it a star like our Sun, yellow and stable, warming a family of planets in a calm and orderly system? Or was it a more dynamic environment? Perhaps a binary star system where two stars orbit each other, creating complex gravitational interactions that could fling objects outward into interstellar space? We may never know the answer, but we can make some educated guesses based on the object's properties. The presence of organic compounds suggests that its parent system had the raw materials necessary for complex chemistry. Carbon, hydrogen, nitrogen, oxygen, perhaps even more complex molecules that form the building blocks of life as we know it. This tells us that wherever 3I Atlas came from, it was a place not entirely unlike our own cosmic neighborhood. The question of how objects like 3I Atlas are ejected from their home star systems is itself a fascinating area of research. In our own solar system, we have the Oort cloud, a vast spherical shell of icy bodies extending perhaps halfway to the nearest star. These objects are loosely bound to the Sun, and occasionally, gravitational perturbations from passing stars or giant molecular clouds can nudge some of them inward toward the Sun, where they become long-period comets. But the same gravitational interactions can also work in reverse, giving objects enough energy to escape the Sun's gravity entirely and drift off into interstellar space. Astronomers estimate that our solar system has probably ejected far more objects into interstellar space than it has captured. In fact, for every interstellar object that passes through our solar system, billions more must be drifting through the galaxy, invisible to us because they're too far away to detect. We're only seeing the tiniest fraction of what's actually out there, like trying to understand an ocean by examining the few drops that happen to fall on your windowsill. What makes this discovery truly remarkable is the realization that interstellar space is likely filled with objects like 3I Atlas. Fragments and debris from planetary systems all across the galaxy, mixing and traveling for millions of years, carrying the chemical signatures of countless different stellar environments. Each star system is constantly exchanging material with the galaxy at large through this process. In a very real sense, the galaxy is not a collection of isolated star systems, but rather a vast, interconnected network where material and, potentially, even life itself could spread between the stars over cosmic timescales. This idea, called panspermia, has been around for over a century, but the discovery of interstellar objects like Oumuamua, 2I, Borisov, and now 3I Atlas has given it new relevance. If organic compounds and perhaps even simple life forms can survive the journey between star systems aboard these cosmic travelers, then life might be far more widespread in the galaxy than we ever imagined. As we continue our exploration into the heart of this mystery, we must now turn to one of the most perplexing aspects of the 3I Atlas story: NASA's peculiar response, or rather, lack thereof. In the age of social media and instant communication, we've grown accustomed to NASA sharing exciting discoveries with the public almost as soon as they happen. Stunning images from the James Webb Space Telescope are released with great fanfare. New findings about Mars or the outer planets generate press releases and media coverage. Even relatively minor astronomical events are often highlighted on NASA's various platforms. But with 3E Atlas, there has been an unusual degree of silence. The initial discovery was announced, of course. These things can't be kept entirely quiet in the modern astronomical community. But beyond the basic confirmation that an interstellar object had been detected, NASA has been remarkably tight-lipped about the details. Official statements have been brief and carefully worded, emphasizing the need for continued observation while saying little about what those observations have revealed. This silence has not gone unnoticed. Amateur astronomers with powerful backyard telescopes have been tracking 3I Atlas, sharing their observations online and comparing notes. Independent observatories not directly affiliated with NASA have published papers discussing various anomalies in the object's behavior. Science journalists have written articles questioning why more information isn't being shared with the public. Some have speculated that NASA is simply being cautious, waiting until they have more data and can be certain of their findings before making any dramatic announcements that might later need to be retracted. This would be perfectly reasonable. Science, after all, is a careful and methodical process. And jumping to conclusions based on preliminary data can lead to embarrassment and confusion. But others point out that NASA has never been quite this cautious before, even with discoveries that were just as strange and uncertain. The level of silence around 3I Atlas seems to be in a category of its own, suggesting that something about this particular object has prompted an unusual degree of discretion. What we're about to discover will make you question everything you thought you knew about how scientific information is shared with the public. Because it's not just NASA that's being quiet. Other space agencies and major observatories around the world have also been notably restrained in their public communications about 3I Atlas. The European Space Agency, which operates several sophisticated observatories and has been involved in observing the object, has released technical data but little in the way of analysis or interpretation. Major university-affiliated observatories have published observational data in the usual scientific journals. But many of the astronomers involved have been unusually reluctant to discuss the implications in interviews or public forums. This coordinated reticence is remarkable in the modern era of astronomy, where scientists are typically eager to share their excitement about new discoveries and where competition between research groups often leads to public debates about the interpretation of data. When the entire community seems to be holding back simultaneously, well, it makes you wonder what they might know that they're not saying. Let's take a moment to imagine why such caution might be warranted. Suppose the data on 3I Atlas revealed something genuinely anomalous, something that didn't fit into any existing framework of natural astronomical phenomena. The responsible thing to do would be to check and double-check everything before making any public statements. You would want to rule out instrument errors, software glitches, misinterpretations of the data. You would want to build up a comprehensive data set from multiple independent sources so that you could be absolutely certain you weren't seeing an artifact or anomaly unique to one particular telescope or detection method. You would want to consult with colleagues, run simulations, explore every possible conventional explanation before even considering more exotic possibilities. And perhaps most importantly, you would want to coordinate your messaging very carefully, because once something is announced publicly, it takes on a life of its own. In the age of social media, a preliminary finding can be misinterpreted, exaggerated, and spread around the world in hours, creating confusion and controversy that can be very difficult to correct later. But there's another possibility that we must consider, one that's more unsettling. What if the caution isn't just about scientific rigor? What if there are other considerations at play? Throughout history, there have been instances where governments and institutions have controlled the release of information for reasons that go beyond pure scientific methodology. Sometimes this is justified. Revealing the capabilities of certain detection systems might compromise national security, for example. Sometimes it's bureaucratic. Information gets caught up in review processes and approval chains that delay its release. And sometimes, rarely, but it does happen, information is withheld because those in charge believe the public isn't ready to hear it, or because releasing it might cause panic or disruption. Now, to be clear, there is no evidence that anything like this is happening with 3I Atlas. But the unusual pattern of silence and restraint has led some observers to wonder whether there might be more to this story than we're being told. The implications of this are staggering when we consider what might prompt such unprecedented caution. The astronomical community is generally very open. Scientists build their careers on publishing discoveries and sharing their findings with the world. Withholding data goes against the fundamental principles of scientific inquiry. For there to be such widespread reticence about 3I Atlas, there would need to be compelling reasons that override the normal academic incentives to publish and share. Perhaps the data is simply so strange, so difficult to interpret, that researchers want to be absolutely certain before saying anything publicly. Perhaps there are genuine concerns about causing unnecessary alarm or feeding into conspiracy theories. Or perhaps, and this is where the mystery deepens most profoundly, perhaps what they're seeing is so unprecedented that they're still trying to understand it themselves, still debating what it means, still wrestling with implications that challenge fundamental assumptions about our place in the universe. Scientists have recently uncovered something extraordinary in the detailed spectroscopic analysis of 3I Atlas, and this is where our journey takes us into truly fascinating territory. Spectroscopy. The analysis of light broken down into its component wavelengths is one of astronomy's most powerful tools. When sunlight reflects off an asteroid or comet, the specific wavelengths of light that are absorbed or reflected tell us about the chemical composition of that object's surface. It's like a fingerprint. Each element and molecule has a unique spectral signature. By analyzing the spectrum of light coming from 3I Atlas, astronomers can determine what it's made of without ever physically touching it. And what they've found is intriguing. The spectrum shows the expected signatures of water ice, carbon dioxide, and various silicate minerals, all normal components of comets. But there are also some unusual features, absorption lines that don't quite match any known mineral or ice compound. Some of these features appear in regions of the spectrum associated with organic molecules, the complex carbon-based compounds that form the basis of life as we know it. Now, before we let our imaginations run too far ahead, it's important to understand that organic molecules in space are actually quite common. They've been found in interstellar clouds, in meteorites, in comets from our own solar system, and even in the atmosphere of Saturn's moon Titan. The term organic doesn't necessarily mean biological. It simply refers to molecules containing carbon bonded to hydrogen and other elements. These molecules can form through purely chemical processes without any involvement of living organisms. So the presence of organics on 3I Atlas is not, in itself, evidence of anything extraordinary. What has astronomers intrigued is the specific nature of these organic signatures, the particular wavelengths and patterns they create in the spectrum. Some researchers have noted that certain features are consistent with more complex organic molecules, things like amino acids or nucleotide bases, the building blocks of proteins and DNA. Again, these can form naturally in space without biology, but their presence in such abundance on an interstellar object is noteworthy and deserves careful study. Deep in the vastness of space, organic chemistry is constantly happening. When you have carbon, hydrogen, nitrogen, and oxygen, some of the most common elements in the universe, along with energy sources like ultraviolet starlight and cosmic rays, you inevitably get the formation of organic molecules. In fact, the interstellar medium itself contains a rich mixture of organic compounds, from simple methane to more complex molecules with dozens of atoms. These molecules form on the surfaces of dust grains in cold molecular clouds, where atoms can stick together and react over millions of years. When stars and planets form from these clouds, they inherit this organic chemistry, seeding new worlds with the raw materials that could potentially lead to life. Every star system in the galaxy has gone through this process. So every interstellar object, including 3I Atlas, carries with it a chemical record of the cloud from which its parent star system formed. By studying these interstellar visitors, we're not just learning about individual objects. We're learning about the chemical evolution of the galaxy itself. As we journey deeper into this mystery, we must consider the possibility that 3I Atlas might be more than just a passive chunk of ice and rock. Its unusual acceleration pattern has prompted some astronomers to propose that it might have an irregular shape that creates unexpected aerodynamic, or rather, outgassing effects. Imagine a comet shaped not like a smooth potato, but more like a complex structure with protrusions and cavities. As ice vaporizes from different parts of such an object, the jets of gas might push in unexpected directions, creating acceleration that doesn't align neatly with the object's motion or rotation. This could explain why 3I Atlas's trajectory doesn't quite match simple models. Some researchers have gone even further, suggesting that the object might have internal cavities or chambers where pressure can build up before being released in sudden bursts, like a natural steam engine powered by the sun's heat. Such a structure could produce very unusual acceleration patterns indeed. What makes this discovery truly remarkable is that we have no way to confirm these structural details without sending a spacecraft to visit 3I Atlas. And given its speed and trajectory, that's not currently feasible with existing technology. The object is moving too fast and will soon be too far away for any probe we could launch to catch up with it. This is the frustrating reality of interstellar object astronomy. We get one brief chance to study these visitors as they pass through our solar system, and then they're gone forever. We have to make the most of remote observations, extracting every bit of information we can from the light these objects reflect and emit. It's a bit like trying to understand a car by only being allowed to look at it through a telescope from miles away. You can see the shape and color, watch it move, but you can't open the hood or peek inside. You have to infer everything from external observations alone. Let's take a moment to imagine what it would be like if we could send a probe to 3I Atlas. Picture a small spacecraft equipped with cameras and spectrometers and perhaps even a lander that could touch down on the object's surface. Such a mission would reveal secrets we can only guess at from Earth. We would see the actual shape and structure in exquisite detail. We would be able to analyze the composition directly, perhaps even drilling into the surface to see what lies beneath the outer crust. We would be able to measure the object's magnetic field if it has one, and detect any gases or particles being emitted. Most importantly, we could determine once and for all whether its strange behavior has a natural explanation or whether we might be looking at something more unusual. Such a mission was proposed shortly after Oumuamua's discovery, and there have been renewed calls for something similar for 3I Atlas. But the technical challenges are immense, and the costs would be substantial. For now, we must content ourselves with remote observations and careful analysis, accepting that some mysteries may remain unsolved. The question of artificial origin, the possibility that 3I Atlas might be something other than a natural object, is one that most astronomers are deeply reluctant to discuss publicly. And with good reason. In science, extraordinary claims require extraordinary evidence, and suggesting that an astronomical object might be artificial is about as extraordinary a claim as you can make. The burden of proof is enormous. You would need to demonstrate not just that the object is unusual, but that its behavior cannot possibly be explained by any natural process, no matter how exotic. This is an incredibly high bar to meet, and rightly so. History is full of examples of astronomical phenomena that initially seemed mysterious or even artificial, only to later receive perfectly natural explanations once we understood the underlying physics better. Pulsars, when first discovered in 1967, were so regular in their pulsations that astronomers half-jokingly called them LGM signals, for little green men. They turned out to be rapidly rotating neutron stars, an entirely natural phenomenon, but one so extreme that we hadn't imagined it before observing it. As we continue our exploration of this cosmic mystery, it's worth noting that there is a small but growing group of scientists who argue that we should at least consider the possibility of artificial objects in space more seriously than we have in the past. Their reasoning goes something like this. We know that technological civilizations are possible because we are one. We also know that space is vast and old, giving plenty of time and room for other civilizations to have emerged. If even a tiny fraction of star systems develop technological life, and if even a tiny fraction of those civilizations reach the point where they can send objects or probes into interstellar space, then the galaxy should contain a significant number of artificial objects. Spacecraft, probes, debris from ancient civilizations, perhaps even self-replicating machines that have been spreading across the galaxy for millions of years. The odds that one of these might eventually pass through our solar system are actually not as vanishingly small as you might think, especially when you consider the timescales involved. The solar system has been here for 4.6 billion years. That's a lot of time for something to wander by. This line of reasoning, while speculative, is not unscientific. It's based on what we know about the universe and the laws of probability. The question is not whether artificial interstellar objects exist. If there are other technological civilizations out there, they almost certainly do. But whether we would recognize one if we saw it, and whether any of the unusual objects we've detected might actually be artificial. Most scientists believe the answer is no, that objects like Oumuamua and 3I Atlas, despite their unusual properties, are best explained as natural phenomena that we simply don't fully understand yet. But a few argue that we should at least investigate the possibility seriously, applying the same rigorous scientific methods we would use for any other hypothesis. After all, if there is even a tiny chance that we're observing an artificial object from another civilization, the implications would be so profound that it would be worth the effort to check, even if we ultimately conclude that the object is natural after all. What we're about to discover will challenge our assumptions about what we should expect to see in space. Because here's the thing about artificial objects. They wouldn't necessarily look like the sleek spacecraft of science fiction. An artificial probe that has been traveling through interstellar space for hundreds of thousands or even millions of years would likely be heavily damaged by micrometeoroid impacts and radiation exposure. It might not be functioning at all anymore. Just a dead hulk drifting through space, indistinguishable at first glance from a natural asteroid. Or if it were still functioning, it might operate on principles so different from our technology that we wouldn't recognize the signs of artificiality. Imagine trying to explain a smartphone to someone from the Middle Ages. They might think it's just a polished stone or perhaps some kind of mirror. Similarly, an advanced probe from another civilization might not announce itself with radio signals or obvious propulsion systems. It might be subtle, gathering data quietly, using techniques we haven't thought of, designed to blend in rather than stand out. The implications of this are staggering when we consider what it means for our search for extraterrestrial intelligence. For decades, SETI, the search for extraterrestrial intelligence, has focused primarily on detecting radio or optical signals from distant civilizations. But perhaps we should also be looking at unusual objects in our own cosmic backyard. Perhaps some interstellar objects are worth investigating more closely, not just as interesting natural phenomena, but as potential artifacts from other civilizations. This doesn't mean we should assume every unusual asteroid or comet is artificial. That would be poor science and would likely lead us astray. But it does mean we should keep an open mind and be willing to consider all possibilities, no matter how extraordinary they might seem. As the physicist Philip Morrison once said, "The absence of evidence is not evidence of absence." Just because we haven't found proof of extraterrestrial intelligence yet doesn't mean it's not out there. It might just be that we haven't been looking in the right places or in the right ways. Scientists have recently uncovered something extraordinary about the way 3I Atlas reflects light. And this observation has added another layer to our growing mystery. Photometry, the precise measurement of an object's brightness over time, reveals information about an object's shape, rotation, and surface properties. When astronomers measured 3I Atlas's brightness variations, they expected to see a relatively simple pattern corresponding to the object tumbling through space. Instead, they found something more complex. There appeared to be multiple periodicities, different cycles of brightness variation overlapping each other. This could indicate that the object has a very irregular shape or that it's rotating in a complex way, perhaps tumbling around multiple axes simultaneously. But it could also suggest that the object's reflectivity is changing over time, perhaps because different surface materials are being exposed as ice sublimates away, or perhaps because the outgassing activity is creating patches of dust and debris that settle on different parts of the surface, changing its reflective properties. Deep in the vastness of space, light carries information across the cosmic distances, and This response paused because Claude reached its max length for a message. Hit continued to nudge Claude along. Our job as curious explorers to decode what that light is telling us. Every photon that reaches our telescopes from 3I Atlas has traveled across millions of kilometers, and embedded in that light is a story about where it came from and what it encountered on its journey. By measuring not just the brightness, but also the polarization of that light, the direction in which the light waves oscillate, astronomers can learn even more about the object's surface properties. Polarization measurements of 3I Atlas have shown some unusual characteristics, suggesting that the surface might have a different texture or composition than typical comets and asteroids. Some areas seem to be highly reflective and smooth, while others appear rough and matte. This patchwork quality is interesting because it suggests either a very heterogeneous composition, an object that's essentially a jumble of different materials stuck together, or an object that has been altered by some process that affects different areas differently. As we journey deeper into this mystery, we must confront an uncomfortable truth about the limits of our knowledge. Despite all our sophisticated instruments and analytical techniques, we are fundamentally limited in what we can learn about 3I Atlas from remote observations alone. We can measure its trajectory with exquisite precision, but we can't definitively determine what's causing its unusual acceleration. We can analyze its spectrum and identify certain chemical compounds, but we can't be completely sure about the detailed composition or internal structure. We can observe its brightness variations and infer something about its shape and rotation, but we can't see it well enough to know for certain what it looks like. Every conclusion we draw is based on models and assumptions. And while these are the best tools we have, they are not perfect. There is always the possibility that we're missing something. Some crucial piece of information that would make everything fall into place and explain all the anomalies we've observed. What makes this discovery truly remarkable is how it has highlighted the need for better capabilities in detecting and studying interstellar objects. Based on statistical models, astronomers estimate that several interstellar objects probably pass through the inner solar system every year, but most go undetected because they're too small or too faint for our current survey systems to spot. Oumuamua was only discovered because it happened to pass relatively close to Earth. And even then, it was detected on its way out of the solar system, after it had already swung around the Sun. Imagine how many interstellar visitors we're missing. Objects that could teach us invaluable lessons about other star systems, about the chemical composition of the galaxy, about the diversity of planetary system architectures, and perhaps even about whether life and intelligence exist elsewhere in the cosmos. The discovery of 3E Atlas, with all its puzzling characteristics, has energized calls for next-generation survey telescopes that can detect smaller and fainter objects earlier in their passage through the solar system. Let's take a moment to imagine what astronomy might look like in a decade or two if these enhanced survey capabilities are built. New telescopes with larger mirrors and more sensitive detectors scanning the sky continuously could detect interstellar objects weeks or even months before they reach their closest approach to the Sun. This earlier detection would give the scientific community time to organize coordinated observation campaigns, bringing together telescopes across the electromagnetic spectrum to gather comprehensive data. It might even provide enough warning time to hastily launch a small probe for a flyby encounter, grabbing close-up images and measurements that would dwarf anything we can achieve with ground-based telescopes. Some scientists have even proposed the idea of a rapid response spacecraft kept in a ready state in orbit, specifically designed to be redirected at short notice to intercept interstellar visitors. Such a system would be expensive and technologically challenging, but the scientific return could be extraordinary. The implications of this are staggering when we consider how our understanding of the universe has been limited by what we've been able to observe. Every technological advance in astronomy has revealed new wonders that we didn't know existed. When Galileo first pointed a telescope at Jupiter and saw its moons, he opened up a new realm of discovery. When radio telescopes were developed, we discovered pulsars, quasars, and the cosmic microwave background radiation. When X-ray telescopes were launched above Earth's atmosphere, we found black holes and neutron stars. Each new capability has expanded our cosmic horizons. The same could be true for interstellar object astronomy. Right now, we're in the early stages, detecting just a handful of these visitors and struggling to understand what we're seeing. But as our capabilities improve, we may find that interstellar objects are a rich source of information about the galaxy. A natural delivery system bringing samples from other star systems directly to us for study. 3I Atlas, with all its mysteries, might someday be seen as the object that motivated humanity to take this field seriously and invest in the tools needed to study it properly. As we continue our exploration into the heart of this cosmic mystery, we must address the elephant in the room, the question of why NASA and other space agencies have been so reticent about sharing information on 3I Atlas. There are several possible explanations, each with different implications. The most benign explanation is simply that the data is complex and difficult to interpret, and the agencies want to avoid making premature announcements that might later prove to be incorrect. Scientific integrity requires that claims be backed up by solid evidence and rigorous analysis, and that takes time. In the modern era of instant communication and social media, there's tremendous pressure to share exciting discoveries immediately. But rushing to announce something before the analysis is complete can lead to embarrassing retractions and damaged credibility. Perhaps NASA is simply being professionally cautious, waiting until they have a comprehensive understanding before making any major public statements about what makes 3I Atlas so unusual. Another possibility is that there are genuine concerns about public reaction. The history of astronomical announcements includes some cautionary tales. When pulsars were first discovered and their signals seemed so artificially regular, the initial speculation about alien communications generated intense media interest and some degree of public anxiety. When the asteroid Apophis was first calculated to have a small but non-zero probability of impacting Earth in 2029, the resulting media coverage created unnecessary alarm among people who didn't understand the subtleties of probability and orbital mechanics. NASA and other agencies are acutely aware that anything they say about unusual space objects will be amplified by the media, potentially distorted or sensationalized, and could cause confusion or concern among the public. If the data on 3 Atlas is genuinely puzzling and doesn't yet have a clear explanation, agencies might be reluctant to discuss it publicly until they can present a complete picture that doesn't leave room for wild speculation and misinterpretation. What we're about to discover will make you question how much we're really told about unusual astronomical phenomena, because there's also a more concerning possibility. That information is being controlled not for scientific or public welfare reasons, but for other motives that are less transparent. Throughout history, governments have sometimes classified or restricted information related to space observations, usually for national security reasons. Satellite surveillance capabilities, for example, are closely guarded secrets because revealing them might compromise intelligence operations. Could something similar be happening with 3I Atlas? It's hard to imagine what national security concerns an interstellar comet or asteroid could raise. Unless, of course, it's not just a comet or asteroid. If there were any indication, even a remote possibility, that 3I Atlas might be artificial in origin, that would certainly be information that governments might want to control very carefully. The implications of confirming the existence of extraterrestrial intelligence would be profound, touching on everything from religion to philosophy to international relations. It's the kind of information that some might argue should be managed carefully and revealed gradually, rather than announced abruptly. Now, to be absolutely clear, there is no confirmed evidence that 3I Atlas is anything other than a natural interstellar object. And there is no proof that any government is suppressing information about it. The reticence we've observed from NASA and other agencies can be adequately explained by the reasonable desire to be scientifically rigorous and avoid public confusion. But the pattern of silence has been unusual enough that it has prompted questions and speculation. And in the absence of clear communication from official sources, people naturally wonder what's being left unsaid. This is why transparency in science is so important. When researchers and institutions are open about their findings, including their uncertainties and the limits of what they know, it builds public trust and understanding. When there's a perception that information is being withheld or carefully controlled, it breeds suspicion and conspiracy theories, even when there's nothing actually being hidden. Deep in the vastness of space, 3I Atlas continues its journey, indifferent to the debates and speculation it has generated here on Earth. It's moving away from the sun now, gradually receding back into the cold darkness of interstellar space, where it will travel for perhaps hundreds of thousands of years before approaching another star. Every day that passes, it becomes a bit fainter, a bit harder to observe, as the distance increases and the amount of sunlight it receives diminishes. Soon, It will be beyond the reach of all but the most powerful telescopes, and eventually, it will fade from view entirely, becoming once again just another invisible piece of cosmic debris drifting through the galaxy. Our window of opportunity to study this object is closing, and that adds urgency to efforts to gather as much data as possible while we still can. Every night of telescope time is precious. Every spectrum could reveal something new. Every image might capture some detail that provides a crucial clue to understanding this enigmatic visitor. As we journey deeper into this mystery, we should consider what lessons we might take from the 3I Atlas saga, regardless of what the final explanation for its unusual behavior turns out to be. One clear lesson is that the universe is more diverse and complex than our models account for. We tend to think we understand comets and asteroids fairly well. They're simple objects, right? Just chunks of rock and ice following predictable orbits. But every time we look closely at one of these objects, we find surprises. Every comet is different, with its own unique characteristics and behaviors. Asteroids come in a bewildering variety of compositions and structures. And when we extend our observations to interstellar objects, things that formed in completely different stellar environments under different conditions, we should expect even greater diversity. Perhaps the unusual characteristics of 3I Atlas are simply showing us that our understanding of what's normal for such objects is too narrow, based as it is on a tiny sample size of objects we've been able to study closely. What makes this discovery truly remarkable is how it reminds us of how much we still have to learn about the cosmos. Despite all our advances in astronomy, all our sophisticated instruments and theoretical models, we are still very much in the early stages of understanding the universe. Each new discovery opens up new questions. Each puzzle we solve reveals new mysteries lurking beneath. This is not a failure of science. It's exactly how science is supposed to work. We build models based on the data we have. But we remain open to the possibility that new observations might require us to revise or even completely rethink those models. The history of science is full of such revolutions. Moments when new data forced us to overturn long-held assumptions and develop entirely new frameworks for understanding nature. Perhaps 3I Atlas is the beginning of such a revolution in our understanding of interstellar objects. Or perhaps, once we gather enough data and analyze it carefully, we'll find that it fits comfortably within our existing knowledge, and the apparent anomalies will dissolve under closer scrutiny. Let's take a moment to imagine the future. Not just the near future of the next few years, but the more distant future of decades or centuries from now. How will humanity look back on the 3I Atlas affair? Will it be remembered as a major turning point in astronomy? The object that revealed something profound about the universe? Or will it be a footnote, an interesting but ultimately not very significant interstellar visitor that briefly captured attention before being surpassed by more dramatic discoveries? We can't know yet. What we can say is that every interstellar object we detect adds to our growing database of information about the galaxy beyond our solar system. Each one is a data point, and as we accumulate more data points, patterns will emerge. We'll begin to understand what's typical and what's truly unusual. We'll develop better theories about how planetary systems form and evolve, how objects are ejected into interstellar space, how they're altered during their long journeys between the stars, and what we might expect to find if we ever develop the capability to travel to other star systems ourselves. The implications of this are staggering when we consider humanity's long-term future in space. Right now, interstellar travel seems like pure science fiction. The distances are so vast and the energy requirements so enormous that it's hard to imagine how we could ever reach even the nearest stars with current or near-future technology. But perhaps, in a few centuries or millennia, our descendants will develop the means to venture beyond the solar system. When they do, the knowledge we're gathering now about interstellar objects will inform their missions. They'll know what to expect in the space between the stars, what kinds of debris fields exist, what hazards they might encounter, what materials they might find that could be useful for resupply or construction. In a sense, by studying objects like 3I Atlas, we're doing reconnaissance for future generations, mapping out the territory they'll someday traverse. It's a long-term investment in humanity's cosmic future, one whose payoff might not come for centuries, but which begins with observations we make today. Scientists have recently uncovered something extraordinary in the study of 3I Atlas's trajectory that bears closer examination. When an object enters the solar system from interstellar space, its path is determined by two main factors: its initial velocity and direction as it enters, and the gravitational pull of the sun and planets. By carefully tracking the object's position over time and comparing it to predictions based on gravity alone, astronomers can determine whether there are any additional forces at work. This is how the anomalous acceleration of Oumuamua was first detected. The object was moving slightly faster than it should have been, based purely on the sun's gravity. With 3I Atlas, the situation is more complex. There does appear to be some non-gravitational acceleration, which isn't surprising for an object showing cometary activity. But the magnitude and direction of this acceleration don't quite match what models predict based on the observed outgassing. It's as if there's something else contributing to the object's motion, something subtle but measurable. Now, this discrepancy might simply indicate that our models of cometary outgassing need refinement. These models make assumptions about how uniformly gas is released from the surface, how the rotation of the object affects the direction of the jets, and how efficiently the outgassing transfers momentum to the comet. All of these factors have some uncertainty, and it's entirely possible that 3I Atlas is simply showing us that the real situation is more complex than our simplified models account for. Perhaps the object has an unusual shape that creates unexpected aerodynamic effects. Perhaps the outgassing is highly asymmetric, with most of the activity concentrated on one side of the object. Perhaps there are internal processes, subsurface ice vaporizing and building up pressure before being released in sudden bursts, that create a pattern of acceleration different from what we'd expect from simple surface sublimation. All of these are plausible natural explanations that would account for the observations without requiring any exotic hypotheses. Deep in the vastness of space, the laws of physics operate with perfect consistency. And yet the outcomes of those laws can be surprisingly complex and varied. A simple object like a comet, subject to nothing more than gravity and the effects of solar heating, can still exhibit behavior that's difficult to predict precisely because the details matter so much. Small variations in composition, shape, rotation rate, or surface texture can lead to significantly different observable outcomes. This is why planetary science is so challenging. We're not dealing with idealized spheres in vacuum moving under gravity alone. We're dealing with irregular, heterogeneous objects with complex surfaces and interiors, subject to multiple competing forces, evolving and changing as they move through different environments. Every object is unique, and general models can only take us so far before we need detailed, object-specific analysis to understand what we're seeing. 3I Atlas is teaching us this lesson once again, showing us that even after decades of studying comets and asteroids, we still have much to learn about these deceptively simple-seeming objects. As we continue our exploration of this cosmic mystery, we must also consider the possibility that 3I Atlas's unusual characteristics might be telling us something important about conditions in its parent star system. The chemical composition of an object carries information about where and how it formed. The ratio of different isotopes, variants of the same element with different numbers of neutrons, can reveal the temperature and pressure conditions during formation. The abundance of various organic molecules suggests what kinds of chemistry were happening. The presence of certain minerals indicates what materials were available in the protoplanetary disk from which the object condensed. By carefully analyzing all these chemical signatures, astronomers can essentially do archaeology on 3I Atlas, reconstructing aspects of its history and origin, even though we'll never be able to visit its parent star system directly. What we're about to discover will amaze you, because this chemical archaeology has revealed some genuinely interesting things about 3I Atlas. The isotopic ratios of hydrogen and oxygen, which can be measured from spectral features of water, suggest that the object formed in a region of its parent star system that was colder than the region where Earth formed. This makes sense. In our own solar system, objects that formed farther from the Sun retain more volatile materials and have different isotopic signatures than objects that formed closer in. But there are also some peculiarities in the ratios of carbon and nitrogen isotopes that don't quite match what we see in our solar system's comets. This could mean that the star around which 3I Atlas formed had a slightly different composition than our Sun. Perhaps it was slightly richer or poorer in certain elements, or it could mean that the chemical processes in that distant protoplanetary disk operated somewhat differently than they did in ours. Each of these possibilities tells us something valuable about the diversity of planetary systems in the galaxy. The presence of complex organic molecules is particularly intriguing from an astrobiological perspective. While these molecules don't indicate life, they can form through non-biological chemistry. They are nonetheless the building blocks from which life could potentially emerge. The fact that they're present on an interstellar object confirms that the chemistry necessary for life is not unique to Earth or even to our solar system, but rather is a common feature of the galaxy. Wherever there are stars and planets, there are likely to be organic molecules, because the elements and physical processes that create them are universal. This doesn't tell us whether life is common in the universe. That depends on many other factors beyond just having the right chemistry. But it does suggest that the raw materials for life are widespread, scattered throughout the galaxy on countless objects like 3I Atlas, drifting through interstellar space, occasionally falling onto planets where, under the right conditions, they might contribute to the emergence of living systems. Let's take a moment to imagine the journey that 3I Atlas has taken to reach us. It likely formed billions of years ago in a protoplanetary disk orbiting a young star hundreds or thousands of light years from here. Perhaps it initially orbited peacefully in that distant solar system's equivalent of the Kuiper Belt or Oort cloud, a frozen world far from its sun, existing in a timeless state of cold stasis for hundreds of millions of years. Then something happened. A gravitational perturbation from a passing star, or a giant planet migrating through the system, or perhaps a close encounter with another body. Whatever the cause, 3I Atlas was given enough energy to escape its parent star's gravity and drift off into interstellar space. For hundreds of thousands of years, perhaps millions, it traveled alone through the darkness between the stars, gradually cooling to the ambient temperature of space itself. Just a few degrees above absolute zero, its surface altered by cosmic rays and the occasional impact from interstellar dust grains. And then, quite by chance, its path intersected with our solar system. The odds of any particular interstellar object passing this close to any particular star are vanishingly small. But with hundreds of billions of stars in the galaxy and vast spans of time, such encounters inevitably happen eventually. 3I Atlas's long, lonely journey had brought it to a moment of significance. A brief period of activity as the sun's warmth touched it for the first time in perhaps millions of years, waking it from its cold sleep, causing its ices to sublimate and its surface to become active. And in that brief moment, as it passed through the inner solar system, beings on one of the star's planets noticed it, tracked it, studied it, and wondered about its origins and nature. It's a connection across cosmic distances and timescales, a fleeting intersection of two very different stories, 3I Atlas's ancient journey and humanity's young but growing exploration of the universe. The implications of this are staggering when we consider what it means for our place in the cosmos. We live in a galaxy that is in constant motion, stars drifting in their orbits around the galactic center, objects being exchanged between stellar systems, material mixing and spreading over billions of years. The atoms in our own bodies, forged in ancient stars and scattered through space by supernovae, have traveled unimaginable distances before eventually coming together on Earth to form living beings capable of contemplating their own origins. In this sense, we are all made of stardust, all connected to the larger cosmic story. And objects like 3I Atlas are part of that same story. Messengers from other chapters, bringing news of distant realms we may never visit, but which are nonetheless part of the same grand narrative that includes our own existence. As we journey deeper into this mystery, we approach the question that underlies all of this discussion. What does 3I Atlas ultimately tell us about the universe and our place within it? Regardless of whether its unusual behavior has a conventional explanation or something more exotic. This object has reminded us that the cosmos is vast, ancient, and full of wonders. It has shown us that our solar system is not isolated, but is part of a larger galactic ecosystem where objects, materials, and perhaps even information are constantly being exchanged. It has demonstrated that we still have much to learn about even seemingly simple things like comets and asteroids. And it has sparked our curiosity, inspiring us to ask deeper questions and push the boundaries of our understanding. These are all valuable outcomes, regardless of what the final answer about 3I Atlas's nature turns out to be. What makes this discovery truly remarkable is how it has energized the field of interstellar object astronomy and raised its profile in the scientific community and with the public. Before Oumuamua, interstellar objects were largely theoretical. Astronomers knew they should exist based on models of planetary system formation and dynamics, but none had been definitively detected. Now, with 3 confirmed interstellar visitors in just 7 years, we know these objects are out there, passing through our solar system regularly, and we're developing the capabilities and strategies to detect and study them. Each new detection adds to our growing database and helps us understand what's typical and what's unusual. As more objects are found, the anomalies of 3I Atlas may come to seem less strange, or, alternatively, they may stand out as genuinely unique. Time and continued observation will tell. Scientists have recently uncovered something extraordinary about the rotation of 3I Atlas that adds yet another piece to this complex puzzle. Most asteroids and comets rotate in a relatively stable way, spinning around a single axis like a top. But careful analysis of the light curve data from 3I Atlas suggests that its rotation might be more complex, possibly what's called a tumbling rotation, where the object spins chaotically around multiple axes simultaneously. This can happen when an object has an irregular shape and has experienced collisions or other events that set it spinning in complex ways. Tumbling rotation is actually fairly common among small asteroids, so finding it in an interstellar object wouldn't be particularly surprising. But what is interesting is how the rotation appears to be changing over time. Something that could indicate that the outgassing is affecting the object's spin state, gradually slowing or speeding up its rotation or changing its orientation as jets of gas act like tiny rocket engines, exerting torque on the object. Deep in the vastness of space, even small forces can have significant effects if they act over long enough periods. An object in space experiences essentially no friction. So once it's set spinning, it will continue spinning indefinitely unless some force acts to change its rotation. This is actually how astronomers can learn about the activity on comets, by measuring how the rotation changes over time and working backwards to determine what forces must be acting. For 3I Atlas, the changes in rotation provide a window into understanding the outgassing, where it's happening on the surface, how strong it is, and how asymmetric it is. If the rotation is changing in predictable ways that match models of cometary outgassing, that would be evidence supporting a conventional explanation for the object's behavior. If the rotation changes don't match those models, well, that would be yet another anomaly to explain. Another piece of the puzzle that doesn't quite fit together as neatly as we'd like. As we continue our exploration of this cosmic mystery, we must acknowledge that some questions may never have definitive answers. 3I Atlas will soon be gone, fading into the darkness beyond the reach of our telescopes, taking its secrets with it. We may never know for certain what causes its unusual acceleration, what its detailed composition is, what it really looks like up close, or where exactly it came from. This uncertainty is frustrating for scientists who value precision and proof, but it's also a reminder of the limitations of our knowledge and the vast scope of what remains unknown. The universe is under no obligation to make its mysteries easy for us to solve. Sometimes we must accept that we've done our best with the data available, drawn the most reasonable conclusions we can, and acknowledge the remaining uncertainties honestly. This is not a failure. It's simply the reality of doing science on the frontier of human knowledge. What we're about to discover will stay with you long after this journey ends. Because the story of 3I Atlas is not really about one particular object, but about the larger questions it represents. Are we alone in the universe? What wonders exist in the vast spaces between the stars? How much don't we know about the cosmos we inhabit? These are questions that have haunted humanity since we first looked up at the night sky and wondered what was out there. Every advance in astronomy brings us closer to answers, but also reveals new depths to the mystery. We now know that there are trillions of planets in our galaxy alone, many of them potentially habitable. We know that the building blocks of life are common throughout space. We know that interstellar objects pass through our solar system regularly, carrying information about distant realms, but we still don't know whether life has emerged elsewhere, whether intelligence has evolved on other worlds, whether we might someday encounter evidence of other civilizations. 3I Atlas, with all its enigmatic properties, reminds us of how much remains unknown and how exciting the journey of discovery continues to be. The implications of this are staggering when we consider what future generations might learn. Centuries from now, astronomers will likely have detected and studied thousands or millions of interstellar objects. They'll have developed a comprehensive understanding of the galactic population of these wanderers. Their typical compositions, their range of behaviors, their origins and fates. They may even have sent probes to intercept and study some of them up close, returning samples to Earth or building databases of detailed observations that dwarf anything we can accomplish today. From that future vantage point, 3I Atlas will be a footnote, one of the early detections that sparked interest in the field, but which was superseded by far better data from later observations. And yet, in this moment, with our current limited knowledge, 3i Atlas is significant. A frontier, a mystery, a challenge to our understanding. This is how science progresses. Each generation doing the best they can with available tools, contributing pieces to a grand puzzle that may take centuries to complete. Let's take a moment to imagine what advice we might give to those future astronomers, based on what we're learning from 3i Atlas. We might tell them to always expect the unexpected, to not be too confident in their models and assumptions, because nature has a way of surprising us. We might encourage them to look at anomalies not as problems to be dismissed, but as opportunities for discovery. Because it's the things that don't fit our expectations that often lead to the most important breakthroughs. We might remind them to balance skepticism with open-mindedness, to be rigorous in their methods and careful about claims, but not so conservative that they dismiss legitimate possibilities just because they seem unlikely or unconventional. And we might urge them to communicate openly with the public, sharing both their discoveries and their uncertainties, building trust and enthusiasm for scientific exploration that will ensure continued support for their work. As we approach the end of our journey through this mystery, it's worth reflecting on what we've learned and what questions remain. 3i Atlas is an interstellar object, the third confirmed visitor from beyond our solar system, and it exhibits a number of unusual characteristics that make it difficult to fully explain with conventional models. Its acceleration doesn't quite match expectations. Its composition shows interesting chemical signatures, including complex organic molecules. Its rotation appears to be complex and changing over time. Its light curve shows periodicities that are hard to explain with simple tumbling. NASA and other space agencies have been surprisingly quiet about sharing details and analysis, leading to speculation about why. None of these individual facts necessarily indicates anything extraordinary. Each could have a natural explanation that we simply haven't fully worked out yet, but taken together, they paint a picture of an object that doesn't quite fit our expectations, that challenges our understanding, and that reminds us how much we still have to learn. What makes this discovery truly remarkable is not that we have all the answers, but that we're asking the questions. Every time we detect an interstellar object, every time we puzzle over unexplained observations, every time we push the boundaries of our understanding, we're participating in one of humanity's greatest adventures, the exploration of the cosmos. This exploration doesn't always yield immediate results. It often involves frustration, dead ends, and more questions than answers. But over the long arc of history, this process of discovery has expanded our horizons beyond anything our ancestors could have imagined. We've learned that Earth is not the center of the universe, but a small planet orbiting a typical star in a vast galaxy. We've discovered that the universe is billions of years old and incomprehensibly large. We've found that the same physical laws that govern our daily lives on Earth also operate across cosmic distances and timescales. And we're beginning to understand that our solar system is not isolated, but connected to a larger galactic community through objects like 3i Atlas that drift between the stars. Scientists have recently uncovered something extraordinary that brings our story full circle. The realization that 3i Atlas is not just scientifically interesting, but also philosophically profound. Every interstellar object that visits our solar system is a reminder that we exist within a larger cosmic context. We tend to think of Earth and the solar system as our complete realm. Everything beyond is so distant as to be almost abstract. But these interstellar visitors make the connection tangible. This object that we can observe with our telescopes, that reflects sunlight into our instruments, that follows a measurable trajectory through our skies. This object was formed in another star system, orbited another sun, experienced conditions completely different from anything in our cosmic neighborhood. And yet here it is, briefly intersecting with our realm before continuing on its way. It's a physical connection between worlds, a bridge between the familiar and the unknown, a reminder that the barriers between stellar systems are not as absolute as they might seem. Deep in the vastness of space, countless objects like 3i Atlas are traveling on their own long journeys, each carrying the signature of its origin, each with its own story to tell. Most will never encounter another star system. They'll drift alone through the darkness for millions or billions of years, eventually cooling to the background temperature of the universe itself, becoming invisible even if anyone were looking. A few will, by chance, pass close enough to another star to be perturbed, perhaps captured into a new orbit, perhaps flung out again into interstellar space on a new trajectory. And an even smaller number will pass close enough to a star with intelligent life to be detected and studied, providing that life with a glimpse of the larger galaxy. We are privileged to be living at a time when our technology has advanced just enough to detect these travelers. A century ago, 3i Atlas would have passed through our solar system completely unnoticed. A century from now, we may have the capability to send probes to intercept and study such objects in detail. This moment, right now, is a transitional period where we can see these visitors but can't yet fully understand them. It's a frustrating but also exciting time, full of mysteries and possibilities. As we journey deeper into the synthesis of everything we've explored, we realize that the significance of 3i Atlas extends beyond the scientific details to touch on deeper questions about humanity's relationship with the cosmos. For most of human history, the stars were distant lights, beautiful but essentially incomprehensible. The idea that we could learn anything about them, much less detect objects traveling between them, would have seemed like pure fantasy. But through the patient accumulation of knowledge, through centuries of observation, experimentation, and theoretical development, we've built up an understanding of the universe that allows us to make sense of phenomena that would have been completely mysterious to our ancestors. We can look at the light from 3i Atlas and determine what it's made of. We can track its position and calculate where it came from and where it's going. We can measure subtle changes in its brightness and infer details about its shape and rotation. This capability is one of humanity's greatest achievements. The transformation of the cosmos from an unknowable mystery into something we can study and understand. What we're about to discover will stay with you. The understanding that while we may not have all the answers about 3i Atlas, the very act of asking questions and seeking understanding is itself meaningful. We live in a universe that operates according to consistent physical laws. Laws that we can discover through observation and reason. This makes the cosmos comprehensible, at least in principle, even if many details remain mysterious in practice. The unusual behavior of 3i Atlas doesn't mean the universe is capricious or impossible to understand. It simply means our current understanding is incomplete, that there are phenomena and processes we haven't fully characterized yet. This is not a crisis, but an opportunity, a chance to refine our models, to gather more data, to think more deeply about what we're observing. Every puzzle we solve makes us better prepared to tackle the next one. Every mystery we unravel reveals new questions lurking beneath. This iterative process of discovery is how science works, and it's why astronomy remains endlessly fascinating even after centuries of study. The implications of this are staggering when we think about what mysteries might still await us in the cosmos. If an object as seemingly simple as an interstellar comet or asteroid can puzzle us this deeply, what will we discover when we're able to study even more exotic phenomena? What will we learn when we finally detect clear evidence of life beyond Earth? Whether microbial life in our own solar system or more complex life elsewhere in the galaxy. What will it mean for our understanding of the universe if we ever detect an unambiguous signal from an extraterrestrial intelligence? These questions may seem far removed from the technical details of 3I Atlas's trajectory and composition, but they're connected by a common thread: the recognition that the universe is vast, complex, and full of surprises, and that our current knowledge, impressive as it is still just a tiny fraction of what there is to know. Let's take a moment to imagine how the story of 3I Atlas might eventually be resolved. Perhaps, in a few years, a detailed analysis of all the collected data will yield a natural explanation that accounts for all the observed anomalies. Perhaps astronomers will realize that the unusual acceleration was due to asymmetric outgassing from an irregular-shaped object, exactly as happens with some comets in our own solar system, but harder to model precisely. Perhaps the complex light curve will be explained by a particularly chaotic tumbling rotation, combined with a heterogeneous surface. Perhaps the unusual spectral features will be traced to specific minerals or ice compositions that are rare in our solar system, but common in the region of the galaxy where 3I Atlas originated. If this happens, if all the pieces fall into place and the mystery resolves into a satisfying natural explanation, that will be a success for... This response paused because Claude reached its max length for a message. Hit continued to nudge Claude along.